Okay, off we go. So two quick things. First of all, as usual, don't forget about the attendance quiz, attendance code, blah, blah, blah. Here it is. Make sure to get it done quick. Got about a minute and a half left. Second, 3 cheers for Duke maintenance. Right? They got the AC mostly. I don't think it's, I could be a little cooler, but it's way better than it was on Friday, so that's awesome. Back into the math. So last time we talked about this idea of confusion of variables, right? And this is, I like to call it unforced error, right? I mean, you don't need to make the question hard by doing what is ultimately unnatural when you try to write it as a diagram. Once you write a diagram, right, you should pretty clearly say, obviously these variables all have to be different because they're different, right? So, choose how you write your functions accordingly. So, don't make those kinds of mistakes. Well, that's a special case of what I'm going to call a larger warning. So, basically, the general statement I want to make is don't forget that all we really know how to do is the chain rule for compositions of multivariable vector-valued functions. So, reminder, this is it, right? So, scratching out the distractions, right? But the point is if you have a composition of functions, the derivative matrices simply tell you factors you multiply by vectors to get other vectors. And factors multiply, well, of course they do, right? So, in particular, this is a statement about multivariable functions. And check it out. This sort of intermediate space, the outputs from the first function are literally exactly the same as the inputs to the second function. And furthermore, notice that y1 can't be a function of y2 and stuff like that. Right? So in each stage, the variables have to be independent of each other, and it has to fit this form. Right? Well, okay, we write that down. And roughly speaking, you get these rules right here. And the idea is your diagram needs to look something like this. So, said differently, if you have a composition of functions, you can write a corresponding diagram. And the diagram's helpful, paths and all that. But if what you have to start with is a diagram of which variables seem to be functions of which other variables, it is not at all clear that what you have there is a composition of functions. And in fact, what I have written here, as I have it written here, is not a composition of two multivariable functions. You can entertain yourself with trying to figure out, well, how am I going to make which variables functions of what in ways that satisfy these rules, and you're going to fail. This can't be done. And then let me just further point out, not only do we not know a chain rule for how to address a situation like this, and by the way, these kinds of situations arise pretty naturally. So not only do we not have a chain rule for this, as written right here, what does this even mean? Partial of z1 with respect to x1. Now that does not look like it'd be a hard problem. Let's see here. It would appear that z1 is a function of these three variables, and you'd think that partial with respect to partial with respect to x1 means I'm going to let that be a variable, then I'm going to hold these other two inputs constant. And what's the problem? Well, the problem is that if x1 is a variable and it's allowed to change, and if y1 is a function of this thing that's allowed to change, how can I say this is constant? Right? I don't know what this means. You got to beware writing stuff down if you don't know what it means, right? This is not good. This is a real problem. Okay, so how do we deal with this? Now, there's different ways to go about this, and what I'm about to show you is arguably a little clunky, and nobody actually does this in practice. But I feel like when people do what people typically do in cases like this, they understand what they're doing in a way that what I'm about to show you is kind of subtext in their mind that, well, yeah, of course that's what I meant, right? So when you don't know this, when you haven't thought it through, seeing the way people would typically write down how they would apply the chain rule to a situation like this can be extremely confusing. And the notation is super awkward and arguably ambiguous, maybe even a little misleading. And it can be a real confusing problem. So let me show you how I'd like to deal with this. I think this fixes the problem. Oh, I'm getting ahead of myself. So let's see. Let me zoom. Oh, not like that. Oh, you know what else I can do? Oh, gosh. Hang on. I don't know what I'm... Okay, now I'm lost. Hang on. Yeah, here we go. Okay, I want to go full screen. There we go. Okay. This example that I'm about to do, if you were to just take these equations and kind of produce the corresponding diagram, you would literally get exactly this. For example, you'll notice that in, you look at this equation that says Z1 is a formula involving X1, Y1, and Y2. Well, that gives you this that we already looked at. Right? So you do that for the rest of these equations and you get this diagram. Okay, so how to deal with this? We don't have a chain rule dealt to address this. Roughly speaking, here's what I'm going to do. I'm going to create a new variable. I'm going to put it right there. The formula for that new variable is going to be, it's just x1. And you see that's what I've written down here. I'm going to define this new variable called x1 star. It's just x1. I'm not actually doing anything. It's literally, the formula for it is x1. But by having a variable here that depends only on x1, right, the formula for which is literally x1, now notice we're all good. I have sort of a stage there and a stage there and a stage there, and I can now literally view these to those as the first function and these to those as the second function, and I now have a composition of functions, and we can do our regular chain rule, and everything's fine at this point. So here's what the diagram turns into right here. And you can see my new variable. I created this new variable x1 star, the formula for which is that it's literally x1. Let's see here. Now, respecting the fact that z1 now is no longer allowed to be a function of those variables. That's not, again, no fair. That's not how a composition works, right? Z1 has to be a function only of the things that came before it. I'm going to reconceive of Z1 as being a function of these, one of the inputs for which is no longer x1, now it's x1 star. It's going to plug in. Right, this old equation where Z1 had a dependence on X1, nope, now it's a dependent on X1 star. And we're now going to consider this collection of equations. Throw that one away. Morally equivalent to what I've written down here. It's the exact same thing. How we doing? Everybody okay so far? And again, I have a composition of functions now, and so there's no question as to what the chain rule says. There's no question as to what anything means. What is the partial of Z1 with respect to X1? Well, Z1's there. Partial with respect to X1 is there. Cool. I have 3 intermediate variables, 3 paths. Correspondingly, we write down 3 terms. Nothing to it. It's regular old chain rule. And then you can proceed going on about your business. And now one nice thing comes up, one little convenience. You'll notice that this comes up. That represents this, you might say, little arrow in the diagram. And how does x1 star depend on x1? Well, it's pretty easy. They're the same. Right? So this derivative here is just a factor of 1. That just goes away. Right? And there you go. questions? Everybody see how that worked? Now here's the awkward thing, again, in practice, and I saw situations like this a zillion times as an undergrad, mostly in physics classes, and, again, people will just kind of write down this, except they don't do this move where they write down x1 star. So they'll write it down without this being an x1 star. Now let's just take a moment in awe of the impropriety of what? You're telling me I'm supposed to compute this as, well, seems to be itself plus other stuff? What? Right? That's super confusing. I think that's just unacceptably confusing for me. And so this avoids that problem. And these two different things that, very often get written down with the exact same notations are now conveniently distinct from each other. Check this out. Partial of Z1 with respect to X1 star, very clearly just talking about that single path, that single dependence from the explicit formula for Z1 as part of, not as part of the composition, but as part of that second function. Whereas this right here is the looking at how, Z1's a function of X1, and altogether we have these three separate paths. Right? We have different notations for things that are, in fact, very, very different. And just everything kind of fits, and there's just all sorts of problems disappear. So anyway, heads up for situations like this. You gotta, again, remember that not even though every composition gives you a diagram, not every diagram is a composition, but very often, again, you just kind of introduce a strategically located variable, and you can make it to where now it is actually a composition, and then you just go about your business. Okay. All right. Moving along. So second derivatives. I think the best way to treat this is to just do one. And I'm largely going to just jump in and actually show you an actual such computation. There is a critical point that, to me, makes these much easier to keep track of. The critical point is not clear just yet how this is going to be the critical point, but when the time comes, I think this will be very, very useful. And it's ultimately a pretty simple observation. We've even talked about this before. If you have some function of x and y, you take the partials, the result is another function of x and y, right? So not a deep observation, but this is going to be key in just a moment. Okay, so that said, let's just dive on in. And here's the premise. We have let's see here. Z is a function of x and y. And then we have r and theta are polar coordinates. Now, I'll remind you, you can think of a coordinate system as sort of geometrically in some sense of how do you visualize these coordinates? But I like to think of them as being functions, right? So the usual polar coordinates I like to think of as a function giving x and y as functions of r and theta, right? And we know the formulas. X is r cosine theta and y is r sin theta, right? Everybody happy with that? Okay, the question is to compute now the second partial of z with respect to r. Look, the way I'm going to do that is pretty straightforward, really. I'm going to compute the first partial. We'll talk about those details in a moment. And then I'm going to take another r partial of that r partial. So we're literally going to take an r partial, and then we're going to take another r partial. Okay, so details. How do I do this one? What's the partial of z with respect to r? Okay, well, we have two paths, and thus two intermediate variables, and thus two terms. Good old chain rule, just like last time. No tricky curves on that. We can compute some of this Because after all, we know exactly what x is as a function of r and theta. X is r cosine theta. And the r partial is easy to write down. And likewise here. And then let me also remind you, we have an alternative notation for writing partials. When it's most useful to use one versus the other, I don't know how to quantify that, but sometimes one's more convenient, sometimes the other. I typically like to use the fraction-like notation when I'm writing down the chain rule, but in a moment we're going to find it particularly convenient to write it like this as a subscript. You'll see why in a couple of seconds. Not quite there yet. But anyway, that's just a rewrite. Okay. All right, and reminder, the whole purpose of computing the r partial is so that I can then take another r partial of that r partial. How are we doing so far? Is everybody with me so far? Okay. All right. Okay. Now, I'm a big believer in the diagrams. I've preached that quite a bit so far, but let me do it again. The diagram is essential. Oh my gosh, it keeps track of stuff for you. It answers a lot of questions. And so, for example, oh my gosh, what am I going to do? I've got a product here. Am I going to have to use the product rule? Tempting to think you might have to use it. And by the way, sometimes you have to use the product rule. Absolutely. But the diagram's going to help us out here. Because we're taking an r partial. That means that theta is a constant. And if theta is a constant, then cosine theta is a constant, and sine theta is a constant. And so do I need to use the product rule where I'm taking a derivative of something times a constant? No, it's a constant. You just factor it right on out. Is that cool? And I'm going to give props here to the diagram. The diagram is what reminded me, okay, I'm doing a partial with respect to that. Theta then, one of my other inputs. That's not the variable I'm taking the partial with respect to. Boom, constant. So I'm a big believer in the diagrams. I hope y'all will subscribe to this position. And yeah, all I did, in the next step here is to factor that out and to factor that out. Okay. Now we have a problem. The problem is, how am I going to make sense out of this thing? The r partial of zx. What? All right. Well, it kind of feels like what this is saying is that I'm going to take z, and I'm going to first take the partial with respect to x, and then take the partial with respect to r. So it kind of feels like, maybe, question mark, that this is z xr. Question mark, right? I'm still trying to make sense out of this. You can see why I'd be tempted to write down something like this, right? I claim this is nonsense. Because for that to make sense, I would need to view z as a function of a collection of variables including both x and r. And you're not allowed to do that, right? Those variables, r, theta, x, and y, are not independent of each other. So that's not, you can't, that doesn't make any sense. And again, you can play the game of, if I were to take the x partial, okay, so I'm going to let x be a variable, but I'm going to hold y and r and theta constant. Wait a minute, if r and theta are constant, x is a constant. So what does that even mean? Again, with the you see, this is why we have to trash this, right? This doesn't make any sense. So, warning. Make sure not to write down something that, again, doesn't make any sense. Right? That's a bunch of nonsense. Okay, so what do we do then with this thing? I got to know what that means before we can proceed. And here's the answer. The answer, back up to here. If you have a function of x and y, which we do, z is a function of x and y, So is zx. Zx is also a function of x and y. Zy is also a function of x and y. And if those things are functions of x and y, indicate thusly on your diagram. Zx and zy are functions of x and y. Add them to your diagram. Is that cool? Everybody see what I did there? At this point, the mystery resolved. Forget about that diagram now. Here's our complete diagram. How am I going to make sense out of, let's see here, partial of zx? Well, there's zx. With respect to r, well, there's r. Okay, no problem. I have two paths. That gives me two terms. And altogether, this partial, not the color I wanted. This partial, the chain rule, allows me to rewrite this partial, looking at the paths, looking at the intermediate variables, like corresponding terms. Here's what the chain rule says that thing is. Problem solved. How we doing? Everybody happy with that? Yes.
It's not like would writing it as the partial of z over the partial of x, like, would that be wrong?
I think it's pretty wrong because you got to keep in mind little notations like we have. So z sub x or partial of z over partial of x. Those are notations that suggest we're taking a partial derivative of a function. Ultimately, when you take any sort of a derivative, the thing you're doing it to is a function. And I'm not clear what function you mean, right? If you write down zxr, I mean, again, it's on you to make it make sense. And I'm not seeing it. So you see the problem? Okay. Yeah, so it's just, I claim there's some ugly questions that would need to get answered, and then that's going to be on you. So I say it just doesn't really make sense. Yeah. Are you satisfied with that? Okay. Yeah. Okay. All right. Anybody else? Okay, so it's all over but the shouting. By the way, this is most of the point right here. Most of the point to doing a second derivatives with the chain rule problem is when you write down a new thing like zx, make sure to annotate your diagram. You got to supplement your diagram, keep your diagram up to date, and then when things like its derivatives come up, then you can see exactly what's going on and deal appropriately. Everything else is, kind of some details. Well, let's see here. Let's do the other one real quick. You notice we have partial of zy with respect to r. All right, well, there's zy. Partial with respect to r. There's r. We have two paths, two intermediate variables, two terms. And the chain rule gives us that. Morally equivalent, kind of the same thing. Also, don't forget multiplicative factors come along for the ride, right? It's easy to forget those. When you have questions like this, they do tend to get a little bulky, right? So it gets a little wide, right? So even in this case where it wasn't even such a complicated scenario, you can see the equations go almost entirely across the page. I think there's a lot of value in being careful about how you write things. Use parentheses carefully. This is going to sound silly, right? But try to write legibly. I've seen situations on student work on exams where the mistake the student made was because they couldn't read their own handwriting. Right? This happens. But worse than that, more commonly than that, by having super complicated handwriting or super, hard to read handwriting, students might just not see things leaping off the page at them as well as they really should, right? So try to write clearly, try to use parentheses appropriately, space things out comfortably, right? Again, you don't want to make any unforced errors of, if only I'd been more careful about how I wrote things down, I think I would have noticed that kind of thing. Okay, so everything else is details. Again, we know how to take partials. Oh, wrong color. We know how to take partials. Come on, colors. We know how to take partials of polar coordinate variables. Right? We know how to rewrite stuff like the x partial of zy. That's going to be zyx. And then because the function is c2, I can rewrite that as zxy. And et cetera, et cetera. Everybody happy? All right, so there's a homework exercise y'all are going to do where the setup is the same as this. You're going to start with the same diagram, and the exercise is to do a second partial, but with respect to theta instead of r. And it's pretty similar to what we just did here. The main difference is that when you get down to this stage, this, which came from there, which will have been a theta partial, it won't be cosine theta, and but more to the point, it won't be a constant. And so what you're going to have at that point is that you're taking an a theta partial of two factors, both of which are functions of theta, and so you'll have to use the product rule. But it's just the product. So the product rule is going to show up in the theta calculation that y'all will do on the homework, and it's one extra step of writing down the product rule. Okay. All right. Okay, now I'm going to show you an application of this. Not of that exact example, but of why it would be useful to know how to do second derivatives with the chain rule. And the example I'm going to use comes from this thing called the Laplacian operator. So some of y'all may have seen this before here or there. We're going to use the Laplacian operator for a few things in this class. It's kind of nice examples of various things. And for whatever it's worth, you're going to see the Laplacian operator a tremendous amount in your engineering classes because the Laplacian operator is a critical part of understanding how waves propagate, how heat flows, how electrons behave. Right? All of this stuff, you write it down. You write down the physics of all of these very fundamental natural physical phenomena. The Laplacian operator keeps coming up. Okay. All right, so it's mathematically, in terms of tools for understanding physics, it's a really big deal. And why is something you'll learn about in another class. But why specifically this comes up? That's the physics department's job. So I'm going to make the observation. I'm going to make the claim that this Laplacian can be rewritten in spherical coordinates like this. Now, it's a lot of work to show that works. Now, I am not going to encourage you to do that. It's a tremendous amount of algebra, and I don't know that it's worth it. In fact, I'm not sure that I've ever done that calculation. I may have. Maybe I did, and I'm repressing it. I don't know. But I don't remember ever doing that calculation. Okay. And I think it would be just a tremendous amount of work. Oh my gosh. Okay, but I want to show you, roughly speaking, where did this come? How would you even get started on this? What you would do is you would recognize that we have a sort of a composition, right? If you have a function of x, y, and z, and if you sort of compose with spherical coordinates like this, right? We know how to find sort of composition partials. I know how to compute spherical partials in terms of rectangular partials. But that's not what I want. What I want is to rewrite rectangular partials in terms of spherical partials. Okay? So what we're going to do, what the strategy would be, and if you did decide, if you if you're looking to kill a couple hours, what you would do is you would just write down these spherical partials using the chain rule, just like we did on the previous page. Different details. And then you would have to turn it around, and instead of having spherical partials in terms of rectangular, you just solve for the rectangular partials in terms of the spherical. So let me show you an example of that in action. And by the way, before I do that, I want to come back here. I want to rewrite this equation a little bit. So what we have in this equation that I know y'all are good with, I wrote this as a partial of z with respect to r. Let's reinterpret this as an operator that applies to a function z. This r partial by itself is an operator. It's something that does something to this variable z. And basically, I can do the same over here. I can view all of this together also as something we do to the variable z. And so, all right, well, let's just take a moment to recognize on the left we have an operator applying to z. On the right we have an operator applying to z. They're always the same. I feel like that means that these operators are the same. Forget about z. The z is not the point. Z is just what you're applying these operators to. If this equation works, if these two sides of the equation are always the same, the operators should be the same. And so it looks a little bit weird to do this, but we can look just at the operators themselves, right? And say the operator called partial with respect to r is equal to the sum of these, this combination of operators that I have on the right side of the equation. So anyway, I needed to make that observation. It's just notation, nothing to worry about. Before coming down here and observing that that's what this says. This right here is just the equation on the previous page, just written in terms of operators, and not bothering to write down what it's applying to. So for example, look, I could stick a z on each of these and it becomes exactly the equation on the previous page, but the operators are what we're actually talking about. Is that cool? You feel free to stick a z in on any of those, it makes you feel more comfortable. It's all fine. Okay, so again, we have that on the previous page, and then analogously, we can do something very similar for the theta partial. And notice, just like I was saying up here, when you have the composition partials written in terms of the rectangular partials, which is what I have here, then you could just solve, just sort of turn it around and solve for the rectangular partials in terms of the curved partials. Now, how do you solve for those? Well, it's a little 2x2 system of equations. I'm sure y'all remember how to do your linear algebra. And you can literally just solve. It's like it's a, ax plus by equals c, dx plus ey equals f, kind of a deal. Is that cool? Is everybody think you can do that? It'd be a good little exercise, right, to solve as indicated and confirm that you get these. All right, so that's kind of a this is a palatable analog of what I'm claiming would allow you to do this, which is to rewrite this rectangular partials into these curved partials. That's how you would prove this equation. Okay, and again, don't actually do that. I think that's too much work. Next question, who cares? Right? You're all thinking it. You have your choice between these, right? Oh my gosh, this seems like it'd be hard to deal with. Okay, how about this one? Nobody's impressed, right? This does not look like a good plan. I think I'm going to change your minds on this. So what I'm going to do is I'm going to look at a particular physical scenario. And by the way, this is not cherry-picked. This is pretty representative of a lot of different situations. I'm going to look at a particular physical scenario. We're going to look at both different ways of computing a Laplacian. And then y'all can decide again, which one do you like better. All right. So here we go. We're going to look at gravitational and electric potentials. They have to satisfy an equation like this. This is called Laplace's equation. In particular, you will notice the Laplacian, the Laplacian right there. And anything that you claim is going to be a gravitational or electric potential for either a point mass, point charge accordingly. That thing, whatever you claim works, is going to have to satisfy this equation. Whatever you think is a electric potential, well, its Laplacian had better be 0. Now, I'm going to propose that for a point mass or point charge, whatever, who cares? I'm going to propose this is a solution. Our job now is to confirm that that actually works. So all I got to do is take that, plug it in, do the calculation, right? Okay, so no sweat, but here we go. Again, we're going to take our Laplacian, and I can choose either the rectangular Laplacian or the horrifying looking spherical Laplacian. And into those, I would plug my function f, which again, you can write it in rectangular coordinates or you can write it in spherical coordinates. So take your pick. Which one of these would you rather compute? I think most people are still probably picking this one, right? But let's peer down the road and what do we see happening here? The first thing I see happening is I'm going to have to take a partial of, I have a square root, which I already don't like. It's a square root with a composition because there's a function inside of that unpleasant function. And side note, it's all in the denominator, which means it's going to be fractions all the way through the calculation. Right? So this is looking a little ugly. Doable, right? But then I'm going to have to take a partial of that thing, which means, by the way, the product rule is going to show up in addition to quotient rule, chain rule, power rule, right? And by the way, that's just for the z term. There's also the x term and the y term. So it gets a little big and bulky and tedious, and it is, depends on how big your handwriting is, 1 to 2 pages of dense calculation, which you can do, right? All right, so let's call that plan B. And now let's look at this other one. I claim this is super easy. I claim it's really, really easy, and here's how. Let's look at this factor, this term right here. Okay, all right, deep breath. Okay, I'm gonna have to take a theta partial, then I'm gonna have to take a theta partial of that, and then I'm gonna have to multiply by this mess. Okay, let's do one step at a time. Let's take a theta partial of it. What's a theta partial of that? Oh, there's no thetas in there. It's 0. This whole thing disappears in a puff of smoke. Right? I mean, I like that, right? I like it when stuff disappears in a puff of smoke, right? That's pretty nice. Okay, sweet. Okay, let's go on to the next one. Oh, whoops. My thing always moves around. Okay, let's see here. Here we go. Okay, let's look at this term. Oh my gosh, that looks even worse. Look, I've got to have phi partial, and then I multiply by something, and then I take another phi partial, and then, oh my god. Okay, slowly and carefully. Phi partial. Oh yeah, there's no phis in there either. This whole thing disappears too. Right? That's pretty nice. Okay. All right, and the last one we're going to actually have to do a little. There's no disappears in a puff of smoke immediately. Here, this. If I take a rho partial of k over rho, I get negative k over rho squared. Oh, wait a second. Negative k over rho squared times rho squared. This is a constant. Its partial is then 0, and then all of this disappears also. We're done. We win. Everybody see how that works? All right, so now you get your pick. Now that you've seen how this works out, which one would you rather write down? And I hope you're with me on this one. Right? It's so much easier to work with. And again, this is not a cherry-picked example. Let's just kind of think through, why would this have worked out so well? Well, the thing that made this work out so well was that the function we're applying to doesn't involve 2 of the 3 coordinates. That's what made it work. The function we're interested in only depends on distance to the origin. Now, how common are these scenarios where functions of interest, like gravitational potential, for example, only depend on distance to the origin? Well, that's how gravity works. So, pretty common. Right? What determines, like if you're thinking about, if you have a point charge, right? And you're thinking about electric fields and electric potential and stuff like that. Well, what determines the electric potential at a certain distance from the origin? Well, again, just distance to the point charge. Which, again, you can set the origin wherever you want and make the point of the charge is your origin. That only depends on distance to the origin. This comes up a lot. So the fact that the spherical partial works out so well here, again, this is not a narrow example. This is a very broad example. And so when you're doing physics with let's say electric potentials, and I say who cares? What's the difference? Because structure. If you write down the formula for the electric attraction, and you look at the formula for gravitational attraction, it's the same formula. Just different constants. Right? So as far as the math goes, it's exactly the same. So in any of these kinds of situations, spherical is a good thing to keep in mind. Okay, enough of that. Okay, moving along. So I want to talk about partial derivatives again. We'll get into directional derivatives. We'll see if we'll make it. But anyway, let's just talk about partial derivatives. And I know y'all remember partial derivatives. Been a while talking about it. It's a slope viewed appropriately. It's a factor viewed appropriately. Now here's something we didn't write down, but this is a nice exercise. It's very doable. If you were to look at this composition where f is a function of x, y, and z, and then x, y, and z are functions of t by this little parameterization I have on the inside here. And if you were to write down the chain rule as applies to taking a derivative of this composition, you'll find you get exactly this partial derivative. So that's, like I say, a good little exercise. Why would I care about that? Well, I like how this reads. Let me just read. I'm going to translate this math into English. Right? What this says is a partial derivative is how fast the function changes when you're at the point A and moving with velocity EI. It kind of reads literally as, well, that's one of our intuitions for what a partial derivative is. So I think that's a nice formula in that sense. Good exercise to check that. And then here's another exercise, and this is a lot easier, but claim you can view a partial as this dot product. It's kind of a silly observation at this stage, but this has got all the partials in it. That's what a gradient is. It's got all the partials. And then dotting with a vector that's mostly zeros. The one in a single position will just pick out one of those partials, and in particular it picks out that one. So both of these formulas at the bottom I think are nice exercises. Give them a try. Ask me in office hours if you have trouble with either of these. Okay. All right. Now, the asterisk is that partial derivatives require that you're going in the direction of a standard basis vector. Right? So the fact that all the directions described here, they're all standard basis vectors, that's critical to talk about a partial derivative. Partial derivatives only go along axes. Right? Parallel to axes. That's it. That's all you can do with a partial derivative. Okay. So here's the cool observation, and roughly speaking, the big idea is, yeah, but what is an axis anyway? What is a coordinate system anyway? And ultimately, the point is, it's an arbitrary choice. A couple observations here I'm just going to kind of talk through. But I like to make sense out of this in terms of a physical scenario. This is a hill. We're looking at the same hill on the left and on the right, the exact same hill. I'm just kind of two different ways of thinking about it. Same hill. I'm at the same point, and there's two different vectors, v and w, same exact vectors, v and w. And the point is, you can set up your axes however you like. There's no law that says north is the y-axis. There's not. It's typical. It's common and convenient in a lot of cases. But there's absolutely no mathematical law that says you have to do that. Coordinates, when you set up coordinates, or equivalently, when you set up axes, that's an arbitrary choice that you make to help you get your hands on certain things, but it's not intrinsic to the situation. Things that are intrinsic to the situation are the hill itself, right? That hill was there before we got there, and it's going to continue to be there after we're gone. Directions, right? I can talk about if I'm at this point and I want to say that way, right? I can just point my finger and say that way. I don't need coordinates for that. Right? Does that make sense? Okay. So coordinates are arbitrary. Axes are arbitrary. It's made up nonsense that we do for our own immediate selfish purposes. There's nothing absolute about it. So if we come back up here and say, okay, well, yeah, but this only works. This only makes sense if you're going in the direction of a standard basis vector. Well, I'm going to repeat. Well, what's that? What's a standard basis vector? I claim any unit vector could be a standard basis vector. For example, you take this W here. Well, with my axes set up as I have them drawn on the left over here, well, this is not pointing in the direction of either of those axes, and so for this axis system, that is not a standard basis vector. But that vector, if I were to just say, hey, you know what? I want to set up my axes like this. Now, all of a sudden, that's a standard basis vector. Right? So the nice punchline is, yeah, this only, claiming that these things are all equal to each other, claiming that I can interpret a slope as a factor, let me be careful about how I circle, as a derivative in that way, and that it's, equal to this expression right here. Saying that these four things I have circled in green, that those are always equal. Yeah, but it only works if you're going in the direction of a standard basis vector. Okay, whatever. Any unit vector will work then. Because any unit vector could be a standard basis vector. Everybody good with that? All right, cool. Now, what I do have to be careful about, I can't say partial derivative and then start talking about how everything could be a standard basis vector, because partial derivative presumes you've already set up a coordinate system. It presumes you've got coordinates, specifically xi, you've decided what that means. So this notation is a peculiarity of an already chosen coordinate system. And if you want to free yourself of coordinate systems, well, you can no longer use this term partial derivative. But it's fine, okay. But what you can do then is say, all right, well, yeah, but these green things, I'm just going to give them a different name. And the name I'm going to give them, this is a very standard thing, is directional derivative. And this is the notation we're going to use. And what is that directional derivative? Well, it's these things. It's a slope. It's a factor. It's this expression, if I might need that for whatever reason. It's computed by this formula, which is going to end up being extremely convenient. And so really, this idea of a directional derivative is just a rip-off of the idea of partial derivatives. All the same intuition, just in a different unit vector direction. And we will pick up here next time. I see I'm out of time. All right, so see y'all later. Have a good one.